Okay, let's get started. Am I audible? No? Yeah, B, can you increase the volume? No. Okay, I'll try to talk like this. So now let's see some practicals. So how many of you are aware of OpenCV library? Okay, so 4, 5, 6 people. So for most of this image processing, we'll be using OpenCV library. It's an open source Python library specifically for computer vision. So CV stands for computer vision, and it's an open source. It's called OpenCV. See, historically, OpenCV was originally written in C++, and then later it was converted into Python. So if you go into the OpenCV, yeah, so this gives you a little bit of history. So OpenCV was actually started by Intel in 1999. And it was primarily written in C++, but then later it was converted into Python. So now it supports both languages, C++, and then Python. Okay. So GL you're talking or CF? GL is graphics, maybe something like that, right? So is that yeah, I'm not sure about that. Yeah, it's called computing language. That's thing not related to computer vision. So this is not related to computer vision. It is parallel programming when you will do. Yeah, if you want to do low level programming, then you can use this. Okay. So coming back, first, if you want to install OpenCV Python, then you need some prerequisites that you should have Python installed, probably 3.10 or above. Then you need NumPy, and then you need Matplotlib. I hope you all have some basic Python experience, how to set up Python, virtual environments, doing pip install, some libraries, all those things, right? Okay. Yeah, Colab. Yeah, I will be using Colab only. So if you open Colab, so I think the OpenCV Python might come installed already, but if you want, you can install it by yourself. Let's do that now. So the library is called OpenCV-Python. So if you want to check whether it installed, we can. So currently it is 4.13. Let's follow this. First, let's start understanding very basic operations of images using OpenCV, like loading an image, displaying it, and saving it back. I'm also following the OpenCV documentation as we go along. So in order to load an image, we use a function called cvt.imread. Imread stands for image reading. And it takes certain parameters like whether you want to read the image in color mode, or if you want to read the image in grayscale mode, or you can just leave it as unchanged, which means the image loads including the alpha channel. This alpha channels comes with a certain image format like such as PNG format, which has an transparency channel also encoded along the image inside the image itself. Okay. But for today's session, we will be mostly using JPEG images. So in order to load the image, so we use cv2.imread. I have an image called checkerboard underscore 18 cross 18.png. And I'm just saying that we want to load this image as a grayscale. Okay. And then what I'm doing here is, in order to display the image, there are two ways to do it. Either you can use the OpenCV library to show the image, or you can use the matplotlib to show the or display the image. When you're working in Jupyter Lab or Jupyter Notebook kind of environment, matplotlib is more convenient because the OpenCV library has a function something called as cv2.intro, something like this. So what it does is it opens or displays the image as a separate window. Then it waits for the users respond whether to close the window or not. Typically, it's a little bit inconvenient, but if you're writing some Python script and running it from a terminal, then this cv2.in show is useful. But mostly as a data scientist who are learning all these things, mostly you'll be working on Jupyter Notebook or Jupyter Lab kind of environment. in that the CV2.info doesn't go well with the Jupyter Lab, right? So that's why it's better to use Matplotlib. So that's why here also they show you two ways. One is to use CV2.info, something like this, or you can use Matplotlib to show the or display the image. So that's what I have shown here. So I rent an image. I store the image in this image variable. Then I am displaying the image using matplotlib using a function called imshow. And I'm also specifying the color map as CMap, so that it doesn't assumes that it is an if we don't specify the CMap, then probably the matplotlib assumes that it is an color image, or it takes a grayscale image and then it just adds the blue and other color channels automatically, and then the color information doesn't look correct. So that's why, since it isn't, we know that this image is a grayscale image, and we're specifically mentioning the color map as a gray. So let's run this. So the error came because I didn't change the directory and it was not able to identify this image. So now if you see, right, this is basically a NumPy array. It's a multi-dimensional array. So image is nothing but an NumPy array. And if you just print those image variable, this is how it looks like. It's a two-dimensional array, and each value of an array ranges from 0 to 255. So in this image, we just have a black and white checkerboard kind of pattern. Wherever there is a black, it's just 0. And wherever there is white, it is 255. So that's why you can see, if you just zoom into this image, this is what you will see. Any image, it's just a matrix of numbers varying from 0 to 255. Also, this image has a certain size or shape. So this has 18 cross 18 array, right? So it has 1, 2, 3, 4, 5, 6, all the way up to 18 columns, and then 1, 2, 3, 4, all the way up to 18 rows. So this we call it rows. So each one is a row, and then vertically each one is called as columns. Okay. So this index is 0, 0, and this index is 17, 17. You follow me? So image is nothing but a matrix, a 2D matrix. It has rows and columns of pixels, and each pixel has a value between 0 to 255. And left, the top left is the starting point of an image. It's called 0, 0. And then the bottom right is the last index of an image. It's 18 cross 18, or in this case, it is 17 cross 17. So you can even access the values of an image just by giving some index like this, right? Or if you just do. Okay. So that basically is loading an image, displaying an image. saving the image will come back later, or even if you want to now save this image, you use a function called cv2.write, and the first variable would be is the image that you want to save. In this case, it is image. And let's say if I want to save it as JPEG, then I think I can pass it like this. Yes. First, okay. Then so the image got saved here. Okay. Because I'm in this directory. So I say where it is. Yeah. Okay. Next, yes. So videos will come the later part. Now we read a grayscale image. Now let's try to load a proper color image. So here I have a sample image called Coca-Cola logo, which is nothing but red and white pixels. Then and what I'm doing here is I read that image. Currently it is stored in this image variable called in the variable called image. Um, then I'm trying to display this image using the matplotlib called inshow. Okay, but you can see that I'm doing an additional step before I am displaying that image. So what I'm doing is I'm using a function called cv2.convertColor. Take the image variable that I have created here and then convert that from a BGR to RGB color space. Okay, so this is important, a small thing that you need to be aware of because the OpenCV reads the image always in BGR format. Okay. Blue, green, red. So typically it is expected to be red, green, blue, but for some historical legacy reasons, the OpenCV developers have always implemented it to be in the reverse direction, BGR. I don't know if it is sequential or if it is because the 400 to 700, it goes from blue, green, red. Probably they were two physics obsessed guys who implemented this. I don't know. But typically for common man, we always say RGB. So that's why uh, except OpenCV, all other libraries work on RGB space. So that's why this is an extra step we need to take care that we need to convert the BGR into an RGB format so that the color information is maintained. If I remove this step, the red will look like blue and the blue will look like red. So let's try that for first. Let me see if it runs without error. Okay, so now let's say if I remove this step, convert step right, and I display that, it will look blue. Okay, because it takes the red and displays it at blue. Because we know that we read this has to be red, but if I don't do this conversion, it looks blue, which means that the OpenCV reads always in the BGR format. RGB is a common standard, but OpenCV has been implemented it in BGR format, and still they continue to do the same. For OpenCV alone, BGR is the default format. If you use here, you see I'm using OpenCV library, right, to read it. By default, it reads in BGR format. They use RGB format. Then they have to change a lot of legacy code. Instead, you just give one convert function. Yeah, I don't know. You have to probably.
It's without applying that function, right? We are making red as blue.
Yes.
Actually, you need to have red, but because of this liability, we make it easier.
Yeah.
To be interchanging both the colors.
Yes.
Blue and red.
Yeah, if you read the image in OpenCV library, it doesn't change it, but it reads in a reverse order. Yeah, but it maintains the red as red, blue as blue. Okay, it doesn't confuse that. But the way it, because you have a three-dimensional matrix, right? So you have M cross N cross C, right? That M cross N cross C, the C is 3 will be there, right? 0, 1, 2. Typically, the 0 should be red, 1 should be green, blue should be, sorry, 2 should be blue. You follow me? But when OpenCV reads it, it keeps 0th index as blue and 1 as green and 2 as red. Yeah, when it reads, it just stores it like in that order. But when you display it as, see here, I am using a matplotlib, which is a different Python library, which displays the image in the same order that it has read, which means the 0th matrix, it will read it as a red and 1 as a green and then 2 as a blue. But we already know when OpenCV read it, it reversed the order. So Matplotlib doesn't know that. So it thinks always assumes that the 0 is always red. So that's why we need to do this conversion. Yeah. Order. Yeah. Yes. Yeah. Just to, if you want, I can demonstrate if I using, so sorry, which thing? 1 second. This notebook. Yeah, now also I can share. This one now. Notebook only. Let's say if I am using CV2 library only, then I don't think I need to do this conversion. See again, as I was telling you that uh, Collab doesn't have a CV2.in show, so then you have to use this patch actually. But you can go try it in your home. Maybe you open this notebook in VS Code and try. I think it should work. So here, when you are using cv2.imshow, you don't have to do that conversion. If you see here, I've not done I've not done any conversion here, but it directly displayed it correctly. Okay. Okay. So what are the key takeaways? Images are nothing but an array of pixels, and OpenCV reads the image in BGA format, while most other libraries use RGB, so conversion is necessary. So is a simple way to display images. For more complex visualization, libraries like Matplotlib offer great flexibility. Okay. Then we talked about color spaces, RGB space, HSV space, grayscale. Um, so here we will try to understand that in code. Um, so what I'm doing here is I'm reading a color image called newsland lake.jpg, and it's stored in an numpy array called image newsland bgr. I specifically to put a bgr indication so that we know the order in which it is stored. Now what we can do is each channel can be splitted or separated, and each color channel can be visualized as a grayscale image. An image looks color only when there is three channel information is there. Okay, and each of these channels, red channel, blue channel, and green channel, each is a grayscale image on its own, which means it has just intensity information only from 0 to 255. This one? Yeah, that's a good question. So the shape of this image looks like this: 600 cross 840 cross 3. So this is what I was mentioning before: M cross N cross 3. Okay. So we have M rows, 840 columns, and then we have three channels: red, green, blue. Okay. Um, so if you just print one pixel value, it will have three values, right? Follow me, right? Um, and then what we are trying to do here is we are just splitting those three channel into each separate color grayscale image. Yes, yeah, we can even try to visualize that. Okay.
Yeah.
You can, I can share that image after the class. So here are the images that I have used in this code. So here you can see the first pixel, right? It has 232, 194, 146. These are nothing but RGB values. It's BGR actually. So currently it is in this format, right? This is blue, green, red. Um, so what I have done here is I'm just visualizing this blue channel, green channel, red channel separately here. So this is how the red channel looks. This is the green channel looks. This is the blue channel. So they do not have any sort of an color information. They are just a grayscale image. But when you just put together into a one single RGB image, and this is how it looks like. You can see this bluish region. So here is where the blue channel will be dominant, and here there is a very less red. It's looking very dark here, which means there is very less red in this lake region. Okay. So you can combine them back and then show it as a color image, or you can take a color image and then separate them into each individual grayscale image and then process them independently. But typically what they do is they take a color image and then they convert that into a grayscale image. So that's what we did here, I believe. Yeah. So here, so instead of reading this New Zealand lake as a color image, we can even read them as a grayscale image. Just try. Now, if I print the shape of this image, so here it is just a flat 2D image. There is no any color channels, and I try to draw. So this will look. Yeah, this is what I was saying. If you don't specify the color map in the matplotlib take it like a color image and try to show it as some sort of a weird color map will be applied on it. So that's why it's better to specify that you want to display it as color. Yeah, so what I have done here is I have taken the color image and then converted that into a grayscale image, single channel. So what it will do is it will take this red channel, green channel, blue channel, and then take an average of each and then make it into a single grayscale image. Ah, so for further processing like edge detection, yeah, smoothing, blurring, or segmentation, object detections. For that, we mostly operate in grayscale space. We don't do it in color space. So first step would be is to convert the color image into a grayscale image, and then only you can do further image processing like filtering, edge detection, thresholding, all those things. Yeah, you draw bounding boxes after you detect an object. In order to detect an object, you do some steps like edge detection, thresholding, those kind of things. So those things are done at the grayscale space, not at the RGB color space. So the first step of all image processing will always be to convert a color image into a grayscale image. So this is an average of these three channels. Yeah. Although they look similar, I think, yeah, density is, if you see the mountain rate. So it's basically an average. Take for every pixel location, take the red value, green value, and blue value and divide it by 3 and then just put it over there. Yes. So this will be taken as an input for further image processing or image analysis. Mm. Yes. 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 Um, Sometimes you can also look the image in terms of statistical perspective. So these are the images are nothing but a distribution of intensity values between 0 to 255, right? So if you take 100 cross 100 image, what we have is around 10,000 pixels or 1,000 pixels, I'm not sure. Yeah. So this 10,000 pixels, they have a range between 0 to 255. Now you can create a distribution of the intensity and see how the image looks like. And that is called image histogram. If it is too dark, then all of the distribution will be more towards on the left hand side between 0 to 50 or somewhere in the range. But it's a too bright image, then it will be more towards in the right hand side. Okay. So that's what I'm trying to show here. So what I have done is I have read that color image and then I have split them into channels. So this is basically a a tuple. And then I have colors and channel names. And then for each channel, I am plotting a histogram. So what I have done is I have taken each channel's grayscale image, right, the matrix, and then I am creating a histogram. So this channel is basically a 10,000 values of between 0 to 255. And then I'm just creating a histogram by having some equal bins between 0 to 256. Okay, so this 0 to 256, probably I'll create 10 bins. 0 to 50, 50 to 100, 100 to 150, 150 to 200, something like that. Then I count the total number of pixels which are between 0 to 50 and put it in the first bin. Between 50 to 100 in the second bin. That's how we calculate histogram, right? So likewise, if we do a histogram for every channel, so this is how it will looks like. So you can see the red channel is mostly in this mid-range values. So this doesn't, uh, so it has more values between 100 to 150, right? And blue regions, if you see, there is a lot of high number of pixels between 240 to 250, you see. Okay. So likewise, this is how the histogram looks like. So why we are taking histogram? These are some fundamental insights that we can get from an image. So how the intensity distributions looks like for an image. Let's say if your image is too flat, and which means that the pixels are very evenly distributed across different regions. So you can broadly divide this intensity range into three regions. Probably 0 to 50 or 75 would be a low dark regions. Then 75 to probably 150 or 175 would be a mid region. And then very bright region would be somewhere from 200 to 255, right? So in this case, the sort of it looks little bit, the contrast is not that great, right? So, but if you want to make it a more contrast image so that certain things pops out for your further analysis, then you can do something called as histogram equalization. That is also one of the function in the OpenCV library. You can that call that function called CV2 dot some equalization or something like that. Then it alters the distribution of the intensity pixels and it makes the image more contrast so that it helps in further processing of the image. Okay. Basically, that is about histogram. And then coming to the HSV color space, we talked about how we can convert from RGB to HSV color space. There is some certain mathematical transformation to be applied. Those mathematical transformations is already being implemented as a part of this function. So CV2 has different color conversion functions. So generally you call CV2 dot CVT color, which is color conversion. And then you specify from which color space to which color space you want to convert. In this particular example, we are converting from BGR color space to HSV color space. So which means that the output of this function will be a HSV color space image. So this image underscore HSV is no more a BGR or RGB image. It is an HSV image, which means it still has the same dimension as RGB, that M cross N cross C. But in RGB, the C has 3 channels, and the first channel is either like red, the second is green, and the third is blue. But in this case, the first channel would be hue, the second channel would be saturation, and the third channel would be value. Okay. Now, what we typically do is we take only the hue channel. Okay. And then we know that in hue, all the colors are beautifully separated. The red is separated from green, the green is separated from blue. There is very minimal overlapping. Then you can apply a certain limit. If I want to separate the red color object from green color, then you say you can do a thresholding on the hue channel, saying if it is below 45, then make it white, above 45, make it black, which means it retains only the red object, and then other all objects are blacked out. So likewise, we can do color separation easily in HSV space in compared to the RGB space. Right? Yeah, so that's basically the key takeaway is RGB is the standard color space. Colors are represented as red, green, blue. Grayscale reduces or compress these informations into shades of gray so that it simplifies the information and it helps in the many further downstream image processing task. Then HSV separates the image, the color, that is hue, from its intensity information, so that it is very particularly useful for task involving color manipulation. Okay. Now, coming back to the slides. Next, we will see something called image thresholding. So this is one of very important image processing steps that basically takes in a grayscale image and then converts them into a black and white image. Okay. So there's a difference between a grayscale image and a black and white image. A black and white image has only two possible values, either 0 or 255, black or white. But grayscale has a series of grayscale values from 0 to 255. Why this is useful? Because it would be the second key step in any image processing. So first you read an image. After you read an image, it will be mostly a color image. And then you convert the color image into a grayscale image. Okay, which changes from 0 to 255. And then you have to convert that grayscale image into a black and white image. Okay, and the white region has to be the region which is the region of interest for you, which is where you're going to do further analysis. Like, for example, object detection, you are measuring the size, shape of that object, or you're trying to count the object. All these things are applied directly on the white regions. Okay, so here in this grayscale, everything is overlapping. So there is no separation between the rice grains and the background. Now in the grayscale, I cannot tell how many rice grains are there, or I cannot go and measure the length of the grain. It is not possible. The first I need to convert the grayscale into a black and white image, and all the rice will be white regions now in my black and white image. Okay. Now I can go and count how many white connected regions are there. That will give me my rice count. You can see, but computer cannot. So, so here for humans, it's easy, right? 1, 2, 3, 4, 5, I can easily count. But for computers, you need, they just, yeah, they just look at, okay, give me a certain method that I can go and count this. So we need to, so what we are saying is, we have to separate this rice region from the black. And then for each separated rice regions, I will put one identifier. Suppose there are 50 rice are there in this, then each connected blob of white pixels, I'll assign one number, 1, 2, 3, like that. So I can just scan. I'll go from left to right. And then here I say, hey, here there is a connected pixels of white. All this belongs to the same object. So this is object number 1. Then I go left to right. Then here I see there is a connected region of white pixels. So these all these connected white pixels forms another object. That then I will say it is 2. Likewise, I just scan everywhere and then say there are 50 rice grains out there. Then I can loop through each connected white regions, and then I can measure the area of it, the length of it, breadth of it, whatever you call it. Yeah, we these white pixels, uh, the image is nothing but a matrix of pixels. But I know that this is a rice grain. Now I need to know what are all the pixels in these images belongs to this particular rice grains, which means I try to find a connectivity. Which are all the pixels that are touching each other? They all form one object. Yeah, if there is an overlap, for example, these two rice grains touching each other, right? This actually for computer is one object. For us, we know that it is two rice grain. Until I do something and separate them and then tell them that, hey, this is not one single object. You need to do some further processing and separate them and then assign two identification numbers to these two connected white regions and tell the computer that these are two separate rice grains and not single rice grain. Okay. That needs a little more advanced processing. Sometimes it is easy to separate. This one, it is pretty easy to separate. Sometimes there will be 10 rice grains touching each other. It is impossible to separate them. So what we will do is we will ignore them. Because we know a rice grain is of a certain shape, certain length, certain width, right? When the rice is of like this, then we know that it is not a rice anymore. We just ignore them. So even if it is touching the border, right? We do not know the true length of this rice because half the information is hidden. So what we will do is we will ignore all the rice grains which is touching the border of the image. So that we consider only the image, or sorry, only the rice grains which we know for sure the true length of it or the true information of it. These are all some, uh, how do we call it? Some information is hidden which we do not know. So that's why we need to ignore them. Again, these are all very 15 years back kind of processing, but now in the AI era, everything will be taken carefully. So I don't know if still people are working on such projects, but I'm just telling you, this helps to understand some basics. Okay, so you understand thresholding, right? So thresholding in typical, no, we have a threshold, and below that threshold, we put some numbers, and above the threshold, we put some numbers, right? It's just called binarization or something like that. So in image, we put a threshold called T, and if the pixel value I x comma y is less than or equal to the threshold, then we make it 0 or black pixels. If it is above the threshold, we make it as white. This black is sometimes is called as background. The white is called as foreground. Now there are different types of thresholding. See, if you the thresholding T, right? How do we determine a proper T? So this is not an any arbitrary value, right? So if you look at the statistical view of this image, you can figure that out T very easily. Now, as I told you, the image is nothing but a distribution of intensity values of each pixels. If it is in 100 cross 100 image, then you probably have 10,000 pixels, each have a intensity value between 0 to 25. And let's say if there is a clear separation of background and foreground, you will see a bimodal histogram. You follow me? So you will see if you plot the histogram of these well separated image, you will see one histogram in the lower region of it, the darker region, another histogram in the lighter region. Okay, so then wherever there is the separation between these two histograms, that is your threshold value. You follow me? Something like this. You know bimodal histogram, right? A clearly separated image, then this value, right? This is your. So this region will make it 0. This region will make it. But mostly it won't be like this easy. So this how I draw it here, where I'm just looking at the histogram of the image. I know what is the T value. That is called global thresholding, which means I used one T value applied across all the image. Okay. So this assumes that there is a uniform illumination across all the images. All the images are uniformly illuminated, and there is no there is also a clear separation between the foreground and the background. Typically in industrial machine vision applications, so they design the camera systems in such a way that they get a good separation between the foreground and the background object. So for example, there is a conveyor belt and there are like typical products coming on this conveyor belt, and then they put a camera, and then they also have a very good high-end illumination systems like ring LEDs. So which makes the foreground to be popped up and the background to be suppressed. And there's a very clear separation between the foreground and the background. So in this case, it is easier to apply this global thresholding. But even then, there will be a lot of challenges in applying this global thresholding. If you apply this, you will not get an easy separation between the object and the background because of the inherent non-uniformity in the illumination. So that is where there are some advanced thresholding methods are being applied, and one of them is called adaptive thresholding, which, as the name implies, we don't have any more single thresholding or a global thresholding value. What we do is we separate the region into multiple windows, and for each window we apply different thresholds, which means maybe the top left is more darker, the bottom right is more lighter, then which means that there will be a different threshold value for the bottom right image, and there will be a different threshold value for the top right image. So likewise, you can divide the total image into, let's say, 3 cross 3. There will be like 9 regions. Then you will have like 9 different threshold values for each sub window of the image. In that way, you can achieve a more accurate thresholding than just using a single global thresholding across all the image. Okay. Hmm. Yeah. Now, nowadays we use deep learning models, which we'll come to that later. So for plant disease classifications, they acquire a lot of images of different diseases, and they train a model on these labeled images. They'll say, hey, this is disease A, this is disease B, this is disease A. So these are a very low level, like basic fundamental. Before the deep learning or the AI era, people used to do like this. So they used to hand engineer all these things. Um, so the first they convert that into a grayscale image, they convert that into a binary, they extract something called as features, right? So whatever the plant diseases, they do it manually. So then they extract features. On these features, they say, hey, if the feature is of certain pattern, then they say this is disease A. If the feature is of another pattern, they say this is disease B. Nowadays, you don't need to do that. You just pump in, you just go and collect 100 images for every plant disease and then put it into one deep learning model. Say that, hey, this image is disease A, this image is disease B, that's it. And then the model will learn all these features on its own. So whatever you're doing it step by step, the model does it on its own. So it is no more, you don't have to implement all these steps on your own. So the model is taken care for you. Yeah. Yeah, that is basically when it comes to the AI models. This is not, we are not into AI anymore. I mean, we are not there in yet. We are just learning the basic computer vision. But if you want to train some computer vision model nowadays, you collect images, label them, and then feed them into some model. The model will learn all these features on its own. You don't have to write them on your own. That's it. So now life has become a lot easier. But still, these things are still relevant if you don't have, let's say, a lot of data. You just have 10 images with you and you need to develop a classification method. Then maybe this might be one of the approach to that. Yeah, but then what you, with 10 images, it is too less, I think. That is one thing. Another thing is not always you have the compute budget. You might have just like a very basic Intel i3 processor or something like that. You can't run a deep learning model. Okay, so this is basically um, thresholding. This second important thing after thresholding is something called as convolution. Okay. Um, so convolution is the basic function that is applied in all of these AI models. So have you heard about convolutional neural networks? Probably in some of your previous uh, course, right? What kind of deep learning course you took before? Okay. So for okay, yeah, you already know CNN based marks. So in CNN, right, the name itself says convolutional neural network. So deep learnings are mostly neural network based. So they are just millions and billions of neurons that are deeply connected to each other. Um, so when this neural network was developing somewhere in 1960s or 70s, mostly it was deeply connected, multi-layer perceptron, they call it, right? So you have like a lot of input layers, output layers, and in between there are hidden layers. And then each neuron is connected to every other neuron. Kind of follow me? So those are like you need to basically pass in a series of input, right? Kind of. Sure. So basically, the neural networks are something like, um, possibly, let's say there is one output is something like that. These are all your input values. These are some numbers, right? But we know images like this. This is like one-dimensional vector. This one, right? So this will be, let's say, 500 values. But image is n cross n cross p. So how would you pass an n cross 3 into this? You can flatten this. So this will be like a vector of million pixels. Just imagine how the neural network will look like if you just flatten an image into a million vectors and then pass it into it. It is going to take a long time and it's also not very efficient. So that's why they use a special operation on the image called convolution. Yeah. So basically, convolution is basically that they take one special filter and then they apply it on a small region of an image, and then they move the filter left to right, top to bottom, and then for every sub region, they do a matrix multiplication. That's called convolution, and then they take that value and put it into the new matrix. Okay. Now, what this convolution does is it basically extracts a certain future feature out of that image. It depends on the filter, the type of filter that you use to convolve this image. It can be an edge filter, it can be smoothing filter, it can be some other types of sort of blurring, some sort of sharpening filters. All these before this deep learning era, we use these filters to convert this image and then transform a grayscale image into a H image. So it just extracts those H informations. There are different types of filters like Sobel filter, Canny filter, which is very specially designed, mathematically designed filters that are then just convolved on the image and that basically extract the edge information from this image. Okay. Now, these filters previously there used to be mathematicians, scientists, computer scientists who spends years to come up with some design these filters. Okay. And then we used to apply multiple filters in order to get useful information from these images. But after this deep learning came, all these filters are learned during the training process. You don't have to go and select a filter or design a filter. These filters are designed and learned during the process itself. So it just goes randomly initially some filters, converts the image, goes to the output. Hey, this is not correct. Go and let us adjust the filter. And then it goes then does this 100 times, 300 times, 1,000 times until they say, hey, now I'm able to correctly classify it. And this is what the filter values are. Okay, so there is no need of mathematicians, no need of statisticians, or they all were outdated. So that was the power of deep learning. All these guys, Sobel, Canny, they're all mathematicians and computational scientists. They were like outdated now. So I hope you got the idea of what this image filtering and convolution. Only we also look at the code of this. So this is how that CV2 implements the thresholding. So it takes in an image. You can pass in a threshold value. Okay, and then you can use what should be the um, maximum value if it is less greater than the threshold. Should it be 255 or should it be just one? All those things can be specified in this function. Um, yeah, and then we have the normal global thresholding using CV2 dot threshold, or you can use an adaptive threshold, which basically calculates the threshold value and applies different threshold value for the different blocks of the image automatically. So there are different algorithms or being implemented within this library. So you can just select that method in this adaptive method parameter. So for example, let's run this one by one. I think let's take it slow. So in this, reading the grayscale image rise, um, not a grayscale image. When it reads as an RGB image. And then I'm just converting that RGB color image into a grayscale image. Then here I'm just setting a global threshold value arbitrarily at 127, which is the middle value between 0 and 255. Then I apply the global thresholding onto this grayscale image with 127 as the value. And if it is above 127, it is going to make it as white. Okay. Then here there's a one more method. Instead of passing the global threshold value manually of 127, what we can do is we can apply an algorithm called Otsu thresholding, which determines this value on its own, which means it applies some statistics. So it takes in the histogram of the intensity pixels, and then it determines a threshold value automatically so that it minimize the intra-class variance and maximize the inter-class variance. Okay, here we have two classes. One is the foreground and the background. So it minimizes the variation within the class, and then it maximizes the variation between the foreground and the background pixels. So here I manually set the global threshold as 127. But when I say use Otsu to automatically determine this global, the Otsu came up with a different value. So it came up with a slightly a change in the value that instead of 127, it used 131 because it thinks that that is most optimal time using 127. So this is the output if you apply the global thresholding, and this is the output if you are applying offshoot thresholding. Okay. Again, all these are very fundamentals, and probably you are not going to use these in any of your projects, but this is just for make sure that you have some fundamental understanding. And then here is where we are using adaptive threshold. See here, you can see in this image, right? There is a lot of illumination variations up here. This bottom right is more darker. The top right of it is more brighter. If you apply on global thresholding or even offshore thresholding, getting proper separation of the foreground and the background is very, very challenging. So here I've just explained the context. Let's say this is a music sheet, and if you want to automatically read the musical notes, and which means that the black dark lines are the musical notes and the white is the paper, which is the background, which means I need to separate the black lines from the white paper. If I try to do it through global thresholding, I cannot do it. But see this adaptive thresholding, how beautifully it has separated the musical black lines from the background white paper. This is being achieved by using an adaptive threshold, which means it separates or it divides this image into sub windows, and for each window it determines its own threshold and applies that threshold and then combines back into a one binary image. Okay. Okay, so that is about thresholding. Then we talked about image filtering. In image filtering, there are different types of filtering: edge filtering, smoothing filtering, sharpening, blurring, etc. and etc. And most important one among all of them is edge detection. Um, so for edge detection, what I'm doing is I'm reading an image called tiger, and then always I don't do any image filtering on the color image. I always do it on the grayscale image. So first step would be is to convert the color image into a grayscale image. And after that, you see here I'm doing a little bit of blurring. Why? Because the raw image has a lot of noise in it. Okay. If I apply the edge filtering directly on the raw image, then it has a lot of noisy edges as well. In order to get rid of those noisy edges, first I smoothen it, which means that very weak edges will go away. Only the strong edges will stay. I need only strong edges because that is sufficient for me. So then I apply different edge filters like Sobel, and then with different kernel sizes. You can just play with this. Okay. Um, So here you can see I'm applying dx equal to 1, which means it it identifies the edges on the x-axis, and I can also identify the edges on the vertically. So there are horizontal edges, there are vertical edges. Then we can combine both the horizontal and the vertical edges to get all of the edge informations. Now you can further process it. You can just separate the tiger from the background. You can do many, many things on top of this. Again, I'm telling you in deep learning, so all these things are taken care automatically during the model. But if somebody asks you, right, I don't know, during interview, I don't know if they are still asking this, but I used to ask this. So I used to tell them like what is actually happening within the convolutional neural network. Basically, what convolutional neural network does is it tries to identify the edge information of the object, let's say face. If you're doing some face detections, so it first identifies the edges of your faces, your eyes, your nose, your lips. Then it takes all this edge information and then combines them and then try to identify your face, or even it can do face recognitions, right? Because it can differentiate a one person from another person based on their facial features. These facial features are nothing but your edges of your eyes, nose, ears, all those things, lips, everything. So earlier they used to do this manually by using all this filtering. But nowadays, we just need to feed in data, and the CNN takes care of all these things. And there's a Sobel filter, there's a Canny filter, right? And see, this is how this is what I used to do 15 years back. But so what I do is I take these rice grain images, and then I tries to find the edge of the rice, and then see here wherever it is touching, right? Then we used to do furthermore processing to separate these two touching lines. Okay. So after you do you read in an image, you then convert that into grayscale, and then you either do thresholding and then or edge filtering, and then you have to come from the grayscale space to a black and white space. Okay. Now, you want to come to a black and white space? Because wherever there is white regions, that those are your objects of interest. That is where you are going to apply some furthermore processing to measure the area of the rise or the length of the rise, like that. So that we call it as blob processing, which means each connected white pixels, we call it as blobs, or we sometimes call it as contours. Okay. So then, which means that for every blob of white pixels, you can measure the area, measure the length, measure the shape, um, all those things, mathematical, geometrical operations you can apply on those blob of white pixels. You can't measure an area or length or a shape on a grayscale image. You need to first identify the objects, and those objects has to be connected pixels, connected white pixels. And these connected white pixels, we call it as blobs. Now, in this entire room, everything doesn't become an object of interest. Probably only the humans might become object of interest, or the the- yeah, that also we can do. Like you can separate the humans from the rest of the regions. You can also separate the walls. You can also separate the tables. Yes, yes, yeah. So each can be a separate white region. But suppose if you want to count only how many persons are there in this room, then you need to know the connected white pixels of that persons only. Okay. Then the rest of things you need to consider as black. But let's say if you want to measure the area of the wall alone, suppose if you're doing some painting, you want to estimate the cost of the painting, right? You just take a picture, and then it automatically segments the walls, and it tells you, hey, this is the length and breadth of this wall, and this is the total area, and this for this square feet you need this much of paint, and that would cost this much. At that time, your area of object of interest is no more the persons or the human beings. It's basically the walls. Okay, sure. Just 2 minutes. So based on that, yeah. Okay, so after lunch, we'll continue in this collab only. So we have furthermore few fundamentals to be covered. After that, we will go into the deep learning part. Yeah, I already shared this collab link in the chat. Oh, modified. Okay. I think the modified will get saved in the link. Not sure.
That's fine. Um,